All right. Thank you all for coming. And I really want to say a thank you to AGU and, of course, to NASA for having me and for sponsoring this whole competition. I'm really excited to share this presentation, which is going to talk about GPU acceleration for data visualization of NASA Earth science data and also for machine learning. Earth scientists today have a sort of problem that they never really thought they'd have, which is simply having too much data. Right now, there are about 50 NASA Earth science satellites in orbit, each producing terabytes of data every single day. And I think by 2022, the amount of new data that's actually being produced is going to increase to about 150 terabytes a day. And obviously, even though having more data is great, it doesn't really mean very much unless people can understand it, people can find patterns in it, and people are able to really understand what their data says. The process of actually visualizing data, which I think is essential to the process of understanding data, is already quite complicated. Because this data is so big, there's a lot that has to go into being able to make it small enough and manageable enough to visualize. Originally, when you have data, it's unstructured, it needs to be gridded, it needs to be projected onto a map, and you need to generate these tile pyramids, which are basically lower resolution versions of the original data, which can be viewed on a web browser and manipulated. This process is great, but it's quite slow, it takes a lot of storage, and it's not interactive, meaning that if you want to change details of the data, if you want to view it using a different color map, a different scale, you would like to apply algorithms or resample it, that becomes very, very difficult. At the same time, there are a lot of questions that you'd like to ask about your data. They can be more quantitative in nature as opposed to visualization. This can include seeing time series or exploratory data analysis with clustering, or even applying machine learning algorithms. And because data can be so large right now, because this data can be gigabytes and gigabytes, these algorithms tend to be very slow. If you want to see a time series that spans years and years, it can take hours to compute. And I think that one of the most essential things for really being able to understand data is having a kind of intuitive data exploration process, where as a scientist, you form questions about your data. You say, is there a trend here? In this small part of the world, do I see patterns? Do I see trends? And you can ask those questions, then have them answered intuitively. You can explore and manipulate in a really intuitive and flexible and powerful way. Right now, current methods are all CPU-based, which means that they use this very traditional method of doing computation that iterates over every single data point in an image or in a data set and applies some kind of algorithm. GPUs are a new kind of hardware which allow you to apply algorithms in parallel across all of the data points in your data set. That means that if you want to apply a color map or reproject your data or ask questions like what is the mean or the average or how does this change over time, all of that can be done almost instantaneously because the computations are actually performed in parallel on all of your data. These technologies are widely used today in machine learning and in computer graphics, but they have not been adopted as widely in the earth science community. Fundamentally, that's what this presentation is about. It is presenting a new GPU visualization prototype, a kind of software library that allows you to work directly with raw earth science data. You have new data that has just come down from a satellite. It's unstructured, it hasn't been gridded, it hasn't been processed. And you can simply load that and grid the data. You can project it, you can rescale it. You can choose, for instance, a logarithmic scale instead of a linear scale. You can apply recent machine learning algorithms for visualization or find data analysis and correlation. And all of this can be done extremely quickly and extremely flexibly using this new technology. Questions that currently with technologies like the Science Data Analytics Platform or with NASA Gibbs, things that are either impossible or take a very long time can be done almost instantly. And that speed is what makes, I think, data exploration really powerful and really easy to do. Here's an example using NASA MER sea surface temperature data. All of this data is generated dynamically on the fly at multiple resolutions, and you can view it in a web browser. So these multi-resolution tiles, which before would have to be pre-generated and pre-processed, taking hours and additional storage, can be generated in real time on the GPU. Tiles can also be generated directly from L1 or L2 data, meaning that it doesn't even need to be pre-processed. And that means that you can actually reduce the amount of storage that you need. Here, for instance, you can view this in a logarithmic scale, which is something that's completely impossible now with data that has already been gridded and applied. A color map has already been implied because you're actually working with binned data instead of the raw scientific data. So by working directly with raw data, you're actually able to work with full scientific fidelity while you're building these visualizations. Here's another example where you're actually just able to zoom in a region of interest. And because you're working directly with the raw data, you can view, for instance, the mean, the max, the standard deviation, and the variance of the region that you're viewing in the current view. So simply by zooming in on a region of the map, you're able to ask questions about how does the temperature in this region differ from other parts of the world? How does that change? Here also, for instance, you can apply computer vision filters. This is a Sobel filter, which shows gradients, basically regions in the ocean where there are large temperature gradients. And this can be generated from the raw data just as easily as viewing any other kind of NASA data. So by working directly with raw data, you really have this advantage of being able to manipulate and visualize your data in real time, flexibly and intuitively. As sort of an example of the way that this can be used in Earth science, we're looking at some NASA ocean data. We have the MER sea surface temperature and AVHARR sea surface temperature anomaly, and then a variety of echo products. And we can ask questions about these. We can say, are there correlations in these products? How do they change over time? Are there variants? Are there important differences within different parts of the world? And simply by visualizing it conveniently, we can answer these questions almost instantly. Here is an example. We can ask questions about the El Nino and La Nina effects. So this is part of this climate cycle in the southern Pacific Ocean that occurs off the coast of Ecuador. It's an approximately 4-year cycle where this band off the coast of South America goes through higher than average and lower than average temperature gradients. So in 2015, there was a very intense El Nino period where the temperature was increased by as much as 3 degrees Celsius compared to the average. The advantage of this kind of technology is that you can actually generate this anomaly data, that is, how much does the temperature differ from historic patterns, without pre-computing it. You can simply say, look at past data, look at the current data, and deseason or remove this historic pattern so you can see this dynamic data without actually computing or storing this anomaly data separately. So here, for instance, we have this AVHRR sea surface temperature data. We're off the coast of South America right now. And we can see that all of this data is dynamically generated. So you aren't using gigabytes and gigabytes of additional data. And you can simply zoom in and out dynamically like you could with a NASA product like Worldview. You can see how it looks. You can experiment. You can move around the map and work really flexibly. Here, for instance, we're just jumping day after day. All of this imagery is generated immediately within 100 milliseconds, working from the raw, unstructured data. So rather than taking hours to pre-process and hours to say, how am I going to solve this question? With GPUs, you're able to actually just ask a question and then have an answer. I think that's really essential for visualization. Sometimes you also have more quantitative questions. So you want to say, how has this changed over time? And simply by selecting the region of interest, you immediately have a time series that spans as much as, in this case, about 6 years, or 4 years, excuse me. You can zoom in and you can immediately see that in the later part of 2015, in this specific region of interest, you have a dramatic increase in the sea surface temperature anomaly. Again, all of this is generated just from the raw sea surface temperature data. So we've generated the anomaly data. We are able to zoom in and out. You're able to select regions, ask questions, say, how dramatic is this El Nino effect? Does this occur? And you get those answers very quickly. And so I think that this technology is really a remarkable way of improving the scientific process. Finally, because GPUs are most widely used for machine learning, which has become a huge field these days, with new breakthroughs being done every day in computer vision, anomaly detection, language, video, all of these algorithms are implemented on the GPU, and they can be computed extremely quickly on the GPU. And so because the GPU is actually used as part of the visualization pipeline, new algorithms can just be dropped in and out and applied as part of the process. Here, for instance, you have on the leftmost column this MODIS true color data, which is optical data taken of the whole world almost every day. But there are parts of the world where there actually is no data because a satellite never passed directly over that region. And the remarkable thing is that looking only at the leftmost column, you're able to predict the kinds of values that would occur had you had a satellite over that region. And you're able to fill it in as part of the visualization process. So if you want to see just a beautiful view of the entire world, simply tile by tile in less than 100 milliseconds, you're able to apply these state-of-the-art machine learning algorithms, fill in these details, and view this the whole world with this inferred data. And you can also have more scientifically relevant applications where you infer missing values in data, you find anomalies, you say if you have access to data at different depths in the ocean, you can fill in those gaps by using machine learning. And I think that having this unified pipeline that combines visualization, analysis, and machine learning is, I think, a really essential and powerful combination of these technologies that makes visualization very useful. Finally, and very quickly, this can all be done in the cloud. So you don't actually have to have a GPU yourself. You can simply go to a website and view all of this data dynamically. And in terms of speed and performance, this can be just dramatically faster than anything that exists currently. For generating individual tiles, it can be as much as 100 times faster. Analytics can be as much as 1,000 times faster using this GPU acceleration. So having this whole pipeline is flexible, it's powerful, and I think it allows you to answer questions that are either very difficult to do or to make observations that you might never have thought to make because you're able to interact seamlessly, fluidly, and answer questions almost as soon as you have them. So I want to thank JPL for having me this summer where I did a lot of this work. And then, of course, NASA and AGU for this, sponsoring this competition and for this award and this wonderful conference. So thank you very much.